Hello everyone. So today we will solve some problems from Irodov. We'll be solving two problems. Both of them are standard problems and it is related to rotational motion. So let me define the problem. So in this problem, what we have is we have a disk. Okay. Yeah, we have a disk. It's a rotating disk. Okay. Uh, Initially, this disk was located. This disk's axis was located at the origin. Okay. So let's say this disk's axis was located at the origin. Okay, this is the origin. O. Okay, and there are two cases given in this particular problem. The first case is such that from this state the disk starts moving in such a way that the axis of the disk moves with a constant velocity v along the positive x-axis. Okay, and the disk also has an angular acceleration which is given by beta. Okay, given this information, I need to find out the expression for basically I need to find out the locus of the instantaneous axis of rotation. Okay, so basically I need to find out yx. Okay, wherein yx is a function of y with respect to x. Okay, and here x denotes the x ordinate of the instantaneous axis of rotation and y denotes the y ordinate of the instantaneous axis of rotation. So it's the x ordinate and y is the y ordinate of the center of the instantaneous axis of rotation of the instantaneous axis of rotation. Now since there is this term called axis of rotation which is coming up, I would try and explain some concepts related to rolling. Okay, let's say there is a rolling body. Okay, and instantaneously, let's say its axis has a velocity given by v, and since it is rolling, it also will have an angular velocity which is, let's say, the instantaneous angular velocity, because it's not necessary that the angular velocity would be constant. The rolling body can have an angular acceleration. In such a case, the rolling body will have an instantaneous angular velocity, right? Now, given this condition, I need to find out the velocity of any point on this plane for this rolling body. Okay, let's say I'm considering this particular point. Okay, let's say this is P. Okay, any point on this rolling body will have two components. One would be the translational component and one would be the rotatory component. Okay, the translational component would be of the velocity would be the same as the velocity of the axis of this rolling body, okay, which in this case is equal to v. V is along this direction, okay. Now this is the translational component, and the second one would be the rotational component, right? It will be given by omega cross r, okay. Now omega is also a vector quantity, right? Angular velocity is a vector quantity. It also has a direction which can be defined by the right hand thumb rule. So in this case, since the body is rotating in a clockwise direction, therefore the angular velocity will have a direction which will be inside the plane, right? So if I try to find out the direction of the velocity, the rotational component of the velocity in this case, r is this direction, right? It will be along this direction, right? Omega cross r will be along this direction, okay. So essentially velocity of any point P can be defined as velocity of the axis of the rolling body, okay, which will be the translational component plus omega vector cross r vector, okay. Now why am I explaining this? Because the instantaneous axis of rotation concept is related with this, okay. Since I'm considering that this cylinder is rolling, now let us talk about the point of contact of this cylinder, or let's say the disc, or whatever the rotating rolling body is, with the ground, okay. So this is the point of contact, right? This point of contact can also have a velocity, or its velocity can be equal to 0. Whatever be the case, its velocity can be written as, let's say the axis of rotation is moving with a velocity of v, and the instantaneous angular velocity is omega. So at this particular point, let's say C, its velocity can be written as v, okay, this is the translational component, minus omega into r, where r is the radius of this body, okay. Now this can be equal to 0, this might not be equal to 0, okay. If it is equal to 0, then that case is called pure rolling, okay. And if it is not equal to 0, if Vc is not equal to 0, in that case we have sliding or impure rolling, okay. In case of pure rolling, this point C is the instantaneous axis of rotation as well. So we kind of get a gist of what an instantaneous axis of rotation is. So instantaneous axis of rotation is essentially that axis which has got 0 velocity with respect to ground at any instance of time, okay. So it's an instantaneous thing. It's not necessary that the axis will have 0 velocity, okay, after some time as well, okay. At a particular instance it might have a 0 velocity, okay. So how does this relate to this question? Because in this question we need to find out the locus of the instantaneous axis of rotation, okay. So let me try and draw the situation for this problem, okay. Let me draw the axes. This is my y-axis and this is my x-axis. Initially, since the body was at rest, the instantaneous axis of rotation was the axis of the disk. Okay, but as the body started moving as per the given condition, that the axis of the body was moving with velocity of v, and the body was also rotating with an angular velocity of beta. Okay, so after some time, obviously the body would have reached, let's say, this point. Okay, okay, sorry, sorry. Yeah, so the center of the disk would have reached, let's say, this point. What would have been the x coordinate of the center of the disk? It would have been v into t, right? Now, where would the instantaneous axis of rotation be? If we think about it, in this particular case, wherein the disk has an anticlockwise angular acceleration, and the center of, the axis of the disk is moving along the x-axis with a constant velocity of v, we can be very sure that the instantaneous axis of rotation would be lying always along a line which would be parallel to the y-axis. Why am I saying this? Let me explain that as well. Let's say if I hypothetically say that my instantaneous axis of rotation lies at this point P, is it ever possible? It's not possible, because there would be two components of the velocities for this particular point P, right? One would be the translational component, which is v, and one would be the rotational component, which will be along this direction. The resultant sum of these two vectors is going to be non-zero. It will have a direction. It would have a direction, let's say, somewhere along this line. So since the resultant velocity is non-zero, this point cannot be my instantaneous axis of rotation. Okay, my instantaneous axis of rotation could be here, or it could be here. It cannot be here. Why? Because the translational component is along this direction. The rotational component is also along this direction. Therefore, the sum of these two vectors will not be equal to 0, which means that my instantaneous axis of rotation cannot lie in this region as well. Therefore, my instantaneous axis of rotation has to lie along this direction. Okay, in this region basically. So if I try and explain this to you, let's say my instantaneous axis of rotation is at this point at this time. Okay, it will have two components. One would be the translational velocity, and the second one would be my rotational component, which is omega into y, right? Because this distance is nothing else but y. Okay, the y ordinate of my instantaneous axis of rotation. Okay, basically its coordinate will be x comma y. Okay, now these two components of the velocity are in opposite directions, which means that the net resultant of these two velocities can be equal to 0. Therefore, I am saying that my instantaneous axis of rotation can lie in this, along this line, a line which is parallel to the y-axis. This is my y-axis and this is my x-axis. Okay, so my instantaneous axis of rotation lies along a line which is parallel to the y-axis. Okay, alright. So there are a few equations that can be written given this information. The first equation I think I've always written, which is the x ordinate of the instantaneous axis of rotation. Okay, Now x has been written as v into t. This is my first equation. Okay. And the second equation can be obtained from the condition of the instantaneous axis of rotation. Okay. What is that? The condition is the instantaneous axis of rotation has a velocity equal to 0 with respect to the ground, and it can be written as v minus v minus omega times y, right? Now how do I, let's say this is equation 2, how do I find out the value of omega? Okay, omega can be found by this simple equation, that is omega equal to beta into t, where beta is the constant angular acceleration of the disk. Okay, I think I had already mentioned that this disk had, yeah, I already mentioned that this is the angular, this disk had an angular acceleration. In the anti-clockwise direction. Okay, so this is my third equation. Okay, so what do? I put in the value of omega in here, right, in the second equation. So I get 0 equal to v minus omega, that is beta into t into y, right, and x equal to v into t. Okay, from this I can get the value of t as x by v. Okay, if I put in the value of t in this equation, I get v equal to beta into x by v into y. Okay, from here I get the value of y, which is a function of x, as v square by, sorry, am I making any mistake? Let me check. No, I think it's fine. Y equal to v square divided by beta into x. So this is the expression of y with respect to x. Okay, for the ICOR. So this was my first case. Okay, now let us try and solve the second case. In the second case, it is mentioned that the disk moves with a constant acceleration a along the positive x-axis, but it has a constant angular velocity omega in the anti-clockwise direction. So I'll write down the condition. The first condition is the axis of the disk moves with a constant acceleration a along the positive x-axis. Okay, and it also has a constant angular velocity in the anti-clockwise direction. In this case, I need to find out y in terms of x, which will essentially be a function of x. Okay, just as the previous case. So given this case, let me draw the initial condition. I mean, the initial condition is the same, that the disk was initially placed in such a way that the center of the disk or the axis of the disk was at the origin, and initially it was rest. Initially it was at rest. Okay, so the initial condition of the disk would be something like this, and let's say the final condition is something like this. Okay, yeah, and let me draw the axis. Let's say this is the axis. Okay, and initially this is my y-axis. Okay, all right. As as mentioned in the previous case, I know that in this case also the instantaneous axis of rotation would be along this particular line. Obviously this line would be moving in the x direction, but the instantaneous axis of rotation would not be at a point like this or this. Okay, it would always be along a line which would be perpendicular to the x-axis but parallel to the y-axis. Okay, so this is my y-axis and this is my x-axis. I have already explained why this is the scenario in the previous case. Okay, so this is my, let's say this point is the instantaneous axis of rotation at time t, and it has abscissa x and y abscissa. Okay, now what will x be? X will essentially be this distance, right? That is the distance that the axis of the disk has traveled at time t. Now the axis of disk was moving along the x direction with a constant acceleration of a, and the disk had a constant angular acceleration, angular velocity of omega. Okay, so x can be written as half into a into t square. Okay, this is basically my second law of motion, and the relationship between y and x can be established by the condition for the ICOR. So the velocity of the ICOR is equal to 0. It is equal to the velocity of the axis of the disk, okay, which is the translational component of the velocity, minus omega into y. Okay, now here in this case omega is constant and this velocity is changing. Now what is velocity? Velocity at time t is a into t, okay, minus omega times y. This is equal to 0. Okay, so from this equation I get at equal to omega times y. Okay, now what is t? I can find out the value of t in the terms of x as t equal to 2x by a to the power 1 by 2. Okay, now I can put this value of t in this equation. Okay, I get a into 2x by a to the power 1 by 2 equal to omega into y. From here I get y, which is a function of x, as 2x a square root divided by omega. This is the expression of y with respect to x for the second case. Alright, yeah. This was my first question. Now let us move on to the second question. Now in the second question I have been given a few things. It's been mentioned that there is a cylinder, okay, and it is purely rolling. By purely rolling I mean the point of contact of the cylinder with the ground is my instantaneous axis of rotation. Okay, so this is my ground. Okay, okay, and it has been given to me that the radius of this cylinder is r, and it is moving with a velocity of, let's say, v. The axis of the cylinder is moving with a velocity of v, which means that the translational velocity of the cylinder is v. There are 2 points given to me, point A, which is the topmost point of the cylinder, and there is a point B, okay, which basically lies along the direction of velocity of the axis of the cylinder. Basically, this is my point B, okay. I need to find out the radius of curvature at point A and at point B. This is what I need to find out, okay. Now let us try and define what radius of curvature is, okay. So what exactly is radius of curvature? If I look only at this point A, what would its trajectory be like? It would actually be like something like this, okay. It would be something like this, and similar would be the trajectory of B as well, but there would be some shift because there would be a time wherein B would reach point A as well, okay. So the trajectories are going to be similar, but there would be some shift in the trajectories, okay. But we need to find out the instantaneous radius of curvature, because radius of curvature itself is an instantaneous term. The radius of curvature of A would be different at different points, okay. For example, generally people ask about the radius of curvature in case of projectile motion, okay. So in general people ask this particular question wherein we are asked to find out the radius of curvature of a point which is, let's say, projected with a initial velocity of u and the angle of projection is theta, and we need to, let's say, find out the radius of curvature at the topmost point. How do we find that? So we assume that at the topmost point, whatever be the velocity would be u of cos theta, because at the topmost point there is no vertical component of the velocity, there is only horizontal component remaining, which is u of cos theta, right? In order to find out the radius of curvature at this particular point, we need to assume a circle, okay, and the circle is such that this particle with mass m moves with this particular velocity in this circle with a radius, let's say, r, under the influence of an external force which is mg. Here r essentially defines the radius of curvature. What does this implicate about the trajectory? If my velocity is large, then the radius of curvature would be large. If my velocity is small, the radius of curvature is small, which means that the particle is going to fall very quickly if the radius of curvature is small at a particular point, right? This is simply what it denotes. So this case was for the parabolic motion. We are considering rolling, so the concept would be similar, okay. So yeah, so let us try and find out the velocity of the particle at point A, okay. What would it be? It will have two components, right? The velocity at point A will have two components. The first one would be the transverse component, which is v plus omega into r. Now it has also been mentioned that this cylinder was rolling purely. It means that this point was my instantaneous axis of rotation, okay. We call it instantaneous center of rotation as well, ICOR, okay. I'd already mentioned, right, previously what ICOR is, right? Or instantaneous axis of rotation is, right? It is that point which has got zero velocity with respect to ground, okay. So what is the velocity of this point? It also has got two components. Let's say it is rotating with an angular velocity of omega. It has got two components. This is the translational component and this is the rotational component. It will be omega into r, right? And this should be equal to 0 for this particular point, right? Which means that v equal to omega into r. This is the condition that we need to remember for pure rolling. Now VA equal to V plus omega into R. So this turns out to be 2 times V. So essentially the velocity of point A is twice the velocity of the axis of the cylinder. Okay. Let us find out the radius of curvature of the point at A first. Okay. So as I had already mentioned uh, in the case of projectile motion, that we need to assume that there is a circle along which this particle is moving with this velocity, okay, and the radius of this particular circle would be the radius of curvature of the particle at point A. Okay, so RA is nothing else but radius of curvature at point A. Okay. Now we assume that with this velocity, the particle at point A, let's say the particle has mass m, okay, it moves with a speed to v, okay, under the influence of an external force. Okay, so the external force is mg. Okay, so there are a few equations that can be written with this information. Okay, the equation is m into g, that is the external force, and this external force also acts as a centripetal force. Okay, so the centripetal force is m into v, that is 2v, the velocity of the particle in the circular path, that is 2v square divided by ra. Okay, from here I get one equation that is ra equal to 4v square divided by g. Okay, now this is my first equation. I can write down one more equation. Now with respect to the axis of the cylinder, the particle at point A is moving in a circular path of radius r. Okay, so with respect to the axis of the cylinder, I can have one more equation. Okay, with respect to the axis of the cylinder, what will the velocity of point A be? It will be equal to v, right? Because the translational component will get cancelled, because with respect to ground, the translational component of the axis of the cylinder is v, the translational component of the point A is equal to v. So with respect to the axis of the cylinder, the translational component of the velocity at point A will be equal to 0. So there will only be a rotational velocity, okay, rotational component of velocity, okay, which will be equal to omega r, which is v. Okay, so with respect to this point also, this particle of mass m is moving with a velocity of, with a speed of v in this circular path. Okay, so for this, with respect to this point, I can write down another equation, that is mg, which is the external force on this particle at point A. This is equal to the centripetal force on this particle at point A moving in a circular path of radius r, okay, with respect to the axis of the cylinder. Okay, so this is equal to m into v square by r. So from here I get g as v square by r. Okay, now I just need to plug in this value of g in here. Okay, and from those two equations I get ra as 4 into v square by g is v square by r, v square gets cancelled, I get ra as 4r. So the radius of curvature at point A is equal to 4r. Now I need to find out the radius of curvature at point B. Okay, Now let us study the point B. Now point B also has got two components of velocities. One is transverse and the other one is the rotational component. What is the transverse component? Translational component? It is V, right? What is the rotational component? What will be its direction? It will be along this direction, right? Since this is omega, this is V, this is R, right? So omega into R, it will be along this direction, okay? And the magnitude will be omega R, which is equal to V. The resultant would be along this direction. What will its magnitude be? Root 2 times V. Now in order to find out the radius of curvature at this point B, what do we need to do? We just need to follow the same concept, right? We'll assume that there is a circle with radius RB, where RB is the radius of curvature at point B, okay? And the particle at B is moving along this circle, okay, with a speed root 2 V, okay, under the influence of an external force mg, okay. Now obviously there would be a component of mg which would be acting like my centripetal force, right? Now I need to find out a few angles, right? This angle would be 45 degree, right? The resultant will make an angle of 45 degree with the x-axis. So this angle is 45 degree. Therefore what will this angle be? This angle will be 45 degree, right? And this component of mg will act as a centripetal force. What will that component be? It will be mg cos of 45 degree. So mg cos of 45 degree is my centripetal force, which can be written as m into root 2 v whole square divided by rb. Rb is nothing else but my radius of curvature at point B, okay. Now I get rb as 2v square divided by cos of 45 degree into g. So this turns out to be 2 root 2 into v square by g. Now I know g from the first case, that g is equal to v square by r, right? So I can plug in that value of g as v square by r. V square gets cancelled. I get rb as 2 root 2 v. Let me try and explain this. Now basically this is the answer. This is the answer for the second case. But let me try and explain this particular diagram, right? Now this circle is drawn in such a way that at this particular point B, the velocity is tangential to the circle, okay. You have to draw a circle in order to find out the radius of curvature, but the circle is such that the velocity at that particular point, okay, at which we need to find out the radius of curvature, the velocity at that point has to be tangential to the circle, right? Even in the case of projectile motion, the circle drawn was such that the velocity was tangential to the circle, right? Let's say I need to find out the radius of curvature at this point. The velocity would be along this direction. The circle has to be this way. The force would be this. But there would be a component of force in this direction which would be kind of forcing this particle to move in a hypothetical circle of radius, let's say r, which will be the radius of curvature at this particular point. This radius would be the radius of curvature for the particle at this particular point, right? So this is the concept. Alright, so I hope I made things clear. Alright, bye. By the way, I have one more point. I have this idea. If recent graduates from IIT, not recent graduates, guys who have just entered IITs, because they are bright people. If there is a coordinated collaboration between all the IITians, and the IITians, tend to pick up topics and then make videos of the concepts of the topics and solve some problems and put that up in a collaborated way on YouTube. I think it would be a very good boon, and that way, I think a lot of things can be democratized. Okay, इस पे मतलब जितने भी इंडिक लैंग्वेजेस हैं, वो सारे लैंग्वेजेस में जो रिसेंट आईआईटी के एंट्रेंट्स हैं, जो आईआईटी में घुसे हैं, वो बच्चे अगर बनाते हैं वीडियो, है ना, और यूट्यूब पे डाल देते हैं, तो काफ़ी डेमोक्रेटाइजेशन हो सकता है. नाउ आई एम नॉट सेइंग दैट टीचर्स आर नॉट इंपॉर्टेंट. टीचर्स विल ऑलवेज बी इंपॉर्टेंट. कितना ही एआई आ जाए, कितना ही ऑनलाइन कोचिंग हो जाए, फिजिकल टीचर विल ऑलवेज बी इंपॉर्टेंट. ओके, इन ऑर्डर टू एक्सप्लेन कॉन्सेप्ट्स टू पीपल. कॉन्सेप्ट समझ में आ भी गया बच्चे को ऑनलाइन, तब भी एक टीचर का, फिजिकल टीचर का ज़रूरत होता ही है. दैट इज़ माई बिलीव. ओके, बट एनी वेज, लाइक इफ IITians, if guys who have just entered IITs, if they stand up and if they start making videos and putting up online, especially educational videos, I think that would be a very good boon. That is just my suggestion. That is just an idea, not even a suggestion. Anyways, bye.